Welcome to another episode of Learning. Please like my videos and share them with your friends and colleagues. This is my channel. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that have appeared in the IIT JAM Mathematics exam 2024. In this video, we discuss the solution of a problem from the section Algebra which is related to group theory. And this question is a multiple select question. There may be more than one answer and the question number is 36. This question is suitable for all these examinations. Especially, this question is suitable for the aspirants of CSIR NET and GATE mathematics examination. Right. The given question is the center Z of G of a group G is defined as Z of G is the set of all those elements x belongs to G such that xg is equal to gx for all G belongs to G. So Zg contains those elements which commute with every element of G. Let order of G denotes this mod G like this, denote the order of G. Then which of the following statements is or true for any group G? We are given four options. Option A, if G is non-abelian and Zg contains more than one element, if G is non-abelian and Zg contains more than one element, then the center of the quotient group G by Zg contains only one element. Option B, if order of G greater than or equal to 2, then there exists a non-trivial homomorphism from Z to G. Option C, if order of G greater than or equal to 2 and G is non-abelian, then there exists a non-identity isomorphism from G to itself. Option D, if order of G is equal to P cube, where P is a prime number, then G is necessarily abelian. Right. This is the definition of the center of G, that is Zg. It is the set of all those elements x belongs to G such that xg is equal to gx for all G belongs to G. Let's now discuss the solution of the problem in detail. We have Zg, the center of a group G, defined as the set of all x belongs to G such that xg is equal to gx for all G belongs to G. So Zg precisely contains those elements of G which commute with every element of G. Let's take option A. If G is a non-abelian, Zg contains more than one element and then the center of the quotient group G by Zg contains only one element. We have a counter example. We take the Quaternion group Q8. Consider the Quaternion group Q8 consisting of plus or minus 1, plus or minus I, plus or minus j, plus or minus k. Now Q8 is non-abelian. Why? Because ij is k, ji is minus k, ij is not equal to ji. Q8 is non-abelian. We are familiar with the Quaternion group, right? Now the center of the Quaternion group Q8 is Z of Q8 is plus or minus 1. It's a very simple exercise which you can very easily see. So 1 So 1 commutes with every element of Q8, minus 1 also commutes with every element of that, and no other elements. That's right. That's right. Now, thus, order of the center of Q8 is equal to 2 greater than 1. So, the hypothesis is satisfied. G is non-abelian and ZG contains more than one element. Then the center of the quotient group G by ZG, that is the quotient group G by ZG, is Q8 by the center of Q8. The center of Q8 contains only one element, it says, but how many elements it has, let us see. So the order of Q8 by the center of Q8 is the order of Q8 by the order of the center is plus or minus 1, that is 8 by 2, that is 4. So this says it contains only one element, but whereas it contains 4 elements. So Q8 by Z, the quotient of the Q8, the quotient group Q8 by the center of Q8 is abelian, right? Why? Because every group of order 4 is abelian. Therefore, Q8 by ZQ8 is abelian. We have to consider the quotient group of G by ZG. So, the quotient group of this quotient group. So, the center of this quotient group Q8 by the center of Q8 is itself, that is Q8 by ZQ8. Why? Because Q8 by ZQ8 is abelian. When it is abelian, its center will be the same. So, the center of G is equal to G when G is abelian. So, Q8 by ZQ8 is abelian. Therefore, the center of this one is itself. So, therefore, the center of Q8 by the center of Q8 by the center of Q8 has order of Q8 by ZQ8, that is 4 elements. But whereas it claims only one element. So therefore, the option A is not true. Here we have calculated the quotient group Q8 by ZQ8 and its order is 4. And we know every group of order 4 is abelian. So this is abelian. So the center of this one, the center of this quotient group is itself Q8 by ZQ8 because it's abelian. So the center of Q8 by ZQ8 has how many elements? These many elements, that is order of Q8 by the center of Q8, that is 4 elements. But whereas the option A claims that it has only one element. Thus option A is not true. Right. We move on to option D here itself. If order of G is P cube, where P is prime number, then G is necessarily abelian. We have this counter example, the Q8 itself, you can take it. So order of G is 2 cube, where 2 is prime number. So G is Q8, you take, G is Q8. The order of G is order of Q8 is equal to 8, 8 is 2 cube, where 2 is prime number. We have already seen, we know that Q8 is non-abelian, and the option D says G is necessarily abelian. It's not true. So we take G is equal to Q8 and the order of G is equal to 2 cube, where 2 is a prime number and G is non-abelian. But whereas it says every group of order P cube, where P is a prime number, is necessarily abelian. It is wrong. It is not true. So therefore option D is not true. Agreed. We move on to the next option. We consider option B. If order of G greater than or equal to 2, then there exists a non-trivial homomorphism from Z to G. Right. We have the group, additive group Z plus. and it is a cyclic group generated by 1, correct? And a homomorphism phi Z to G is completely determined by its action phi of 1. Phi of 1 is equal to G for some G belongs to G. So it's completely determined by the action of phi of 1. Then for any integer n coming from Z, we will have phi of n is equal to G power n. Right. If G not equal to E, then phi is non-trivial. Right. The order of G greater than 2, so there will be one element which is non-identity element will be there. Since order of G greater than or equal to 2, there exists a G not equal to E in E. Order of G greater than or equal to 2. There exists a G not equal to. So with this G, with this G, phi of 1 is equal to G will be the homomorphism from Z to G. Thus, there exists a non-trivial homomorphism because G not equal to E. So, phi of 1 is equal to G, G not equal to E, and that will be the non-trivial homomorphism from Z to G. So, there exists such a non-trivial homomorphism. So, the option B is true. So, option B is true. We go to the next option. Option C, right. If order of G greater than or equal to 2, G is non-abelian, then there exists a non-identity isomorphism from G to itself. Isomorphism from G to itself means it is an automorphism. So there exists a non-identity automorphism of G. That is, if order of G greater than or equal to 2 and G is non-abelian, then there exists a non-identity automorphism of G. Given G is non-abelian, correct? Order of G greater than or equal to 2. So when G is non-abelian, the smallest group which is non-abelian is S3, that is its order is 6. Order of G greater than or equal to 2 means it will start from 6 onwards. So anyway, for any G belongs to G, define a map phi suffix G from group G to itself by conjugation. Phi G of X is by conjugation Gx G inverse. Now we will show that phi G is a homomorphism. For all x comma y belongs to G, phi G of xy is Gxy G inverse by definition. This you can write it as Gx G inverse multiplied by Gy G inverse, and that is phi G of x multiplied by phi G of y. So thus phi G is a homomorphism. It's very easy to see phi G is 1, 1. Phi G of x is equal to phi G of y will imply Gx G inverse is equal to Gy G inverse by definition. By cancellation, pre and post cancellations, we'll get x is equal to y, and this will tell you that phi of G is 1 to 1. Phi of G is also onto. How do we show? For each y belongs to G in the codomain, there exists a x is equal to G inverse yg belongs to G in the domain, such that phi G of x is equal to Gx G inverse, that is Gx is G inverse yg into G inverse. So G inverse is identity, it will be y. So thus this shows that every element in the codomain has a pre-image in the domain. Therefore, phi G is onto. And phi G is from G to G, which is a homomorphism, 1, 1 and onto. Thus, it is an automorphism. So thus, phi of G is an automorphism of G. So come back to here. So phi G is an automorphism of G called inner automorphism of G. Now, when this automorphism is non-trivial, so now phi G is non-identity. When this is non-identity, is the Now we say phi g is the identity automorphism if and only if phi g of x is equal to x for all x belongs to G. This is if and only if gx G inverse is equal to x for all x belongs to G. This is if and only if gx is equal to xg for all x belongs to G. This is if and only if G belongs to the center of G. So phi g will be an identity automorphism if and only if G belongs to Zg. If G doesn't belong to Zg, then it will be a non-identity automorphism. For that, since G is non-abelian, when G is non-abelian, Zg is not the whole of G. Therefore, there exists an element G in the group G such that G does not belong to the center of G. Yes, because it is non-abelian, it is not equal to. So for this element G, the inner automorphism phi G is a non-identity automorphism of G. So thus, every non-abelian group has at least one non-identity automorphism. Right. So this shows option C is true. So combining all the options, the answer to this question is options B and option C. Right. That is the detailed discussion of the solution of this problem. And I said that it is a good problem. Good problem. I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Yes, this is my channel. Please subscribe my channel if you have not already subscribed. Yes, I am sure I will be meeting all of you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.